actually, one of the reasons I wear black beside, so I know you can't see my coffee stains, is do you guys know who Johnny Cash was? He was known as the Man in Black, so I took his place. Okay. All right. So we're wrapping up composite functions in section 2.6 of your handout. Right. So we ended yesterday at the bottom of page 3. With example 6. So let's take a look at example 7, page 4, which is sort of an application of composite functions. So we're given the number of bacteria in a refrigerated food is given by this quadratic function. N of t is equal to 20t squared minus 80t plus 500, okay, for temperatures between 2 and 14 degrees Celsius. Okay. When the food is removed from refrigeration, the temperature is given by big T and little t are different variables. Okay? Big T stands for temperature, little t stands for time. And so the temperature as a function of time is equal to 4t plus 2, where time varies from 0 to 3, okay? From 0 to 3 hours. So you can see as time increases, the temperature increases, okay, in Celsius. Find the following: the composite function n of big T of little t, and what does that function represent? So we're taking the composite big N with big T as a function of little t, okay? And that's equal to N of big T of little t. So you know the first step. Replace big T of little t with what it's equal to. And it is equal to 4t plus 2. Right? That's temperature as a function of time. Okay? And now we have to evaluate big N of 4t plus 2. We've got to put 4t plus 2 in for t on the right-hand side here. Wherever we see a t, we have to put 4t plus 2, right? So this is equal to 20 times 4t plus 2 squared, right? Because it's t squared, minus 80 times 4t plus 2 plus 500. Right, so replace big T squared with 4t plus 2 squared, and big T with 4t plus 2 here. And now we get to simplify, okay? So, four t plus 2 squared, you got a FOIL, right? It's 4t plus 2 times 4t plus 2. So when you FOIL that, you verify this, you get 16t squared plus 16t plus 4. And then you got to distribute the minus 80 inside the parentheses. Minus 80 times 4t is minus 320t. Minus 80 plus 2 is minus 160. Continue with the simplification. right? We gotta distribute the 20 inside parentheses here. 20 times 16t squared is 320t squared. 20 times 16t is 320t. And 20 times 4 is 8. Okay? So that's distributing 20 inside parentheses. And then we have the minus 320t. And then we can combine these two constants, right? Minus 160 plus 500 is 340. Now you just combine like terms, right? There's only one term with t squared, 320t squared. And then terms involving t, 320 minus 320t, right? They cancel. And we're left with 80 plus 340, which is 420. So the composite, big N with big T is a function of little t, is equal to 320 little t squared plus 420. Okay? Now we got to give an interpretation for this composite function. Anybody want to venture an interpretation? Remember, big N is the number of bacteria in the frozen food, right? And little t is time. So in the composite, this is the number of bacteria in the frozen food as a function of time. Okay. So we can write interpretation, the number of bacteria. I said frozen food, it actually says refrigerated food, I'm sorry. Okay. The number of bacteria t hours after the food is removed from refrigeration. Okay. So the number of bacteria in the refrigerated food is a function of temperature. And temperature is a function of time after it's removed from refrigeration. So in the composite, right, big N is a function of little t, and we have the number of bacteria in the refrigerated food t hours after it's removed from refrigeration. Okay? Any questions on that? Okay, and B, it asks the number of bacteria in the food when t equals 2. So all we got to do is put 2 in for t, right? On the right-hand side here. So we're evaluating the composite, the big N with big T at little t equals 2, right? We're just putting in 2 in for little t. And so we just put in 2 in for little t here. And we have 320 times 2 squared plus 420, which is equal to 1,700. So 1,700 is the number of bacteria in the food when t, little t equals 2 hours. 2 hours after it's removed from refrigeration. Any questions on that? Okay. Example 8, you're given the graphs of 2 functions, and you have to evaluate these expressions down here, okay, using the information in the two graphs. So in A, we gotta find f of g of 2. Okay. So the first step is to replace g of 2 with what it's equal to, right? So here on the right is the graph of g of x. Remember, this is the x-axis, right? And the vertical axis, right? It's also the y-axis. Okay. And so to find the value of g of 2, right, you go to x equals 2 and see what the y-coordinate is. Well, this is an x-intercept, right? This is the point 2, 0. And so g of 2 is equal to 0. So we have f of 0. Now to evaluate f of 0, graph on the left is the graph of f of x. Again, this is the x-axis. And so what's the value of the function x equals 0? It's the y-coordinate of this point right here, right? What's the y-coordinate? This is the point 0, 1, right? The y-coordinate is 1. So f of 0 is equal to 1. Any questions on how I figured that out? Okay. In B, we got to find f plus g of minus 1. Well, this is equal to, by definition, f of minus 1 plus g of minus 1, right? What's f of minus 1 equal to? Here's the graph of f of x. Here's x equals minus 1. That's an x-intercept, right? So the y-coordinate is 0. So f of minus 1 is equal to 0. What's g of minus 1? So here's the graph of g of x. Here's x equals minus 1 on the x-axis. And here's the point on the graph at x equals minus 1. It has a y-coordinate 3, right? This is the point minus 1, 3. So g of minus 1 is equal to 3. So f plus g of minus 1 is equal to 3. Okay. In C, we got to find the composite of g with f at x equals minus 3. G of f of minus 3. So again, right, the first thing you have to evaluate is f of minus 3. So again, here's the graph of f of x. Here's x equals minus 3 on the x-axis. And here's the point on the graph at x equals minus 3. And that point has a y-coordinate of minus 2, right? So that's the point minus 3 minus 2. And so f of minus 3 is equal to minus 2. So now you got to evaluate g of minus 2. Again, here's the graph of g of x. Here's x equals minus 2. And you can see on the graph of g of x, there's an x-intercept at x equals minus 2. Right? So that's the point minus 2, 0. So g of minus 2 is equal to 0. Okay. All right. So any questions on A, B, and C? Okay. In D, we've got to find the composite of f with itself at x equals 1. So by definition, this is f of 1. So you got to find f of 1. So on the graph of f of x, right here at x equals 1, right? The point on the graph at x equals 1 has coordinates 1, 2. So f of 1 is equal to 2. what's f of 2? Here's the point on the graph at x equals 2. It has a y coordinate of 3, right? That's a point 2, 3. So f of 2 is equal to 3. And then we have in E, we have G minus F of 2, which by definition is G of 2 minus F of 2. Okay. Well, what's G of 2 equal to? Well, here's x equals 2, right? In the graph of G of x, here's x equals 2. You can see that's an x-intercept. The y coordinate is 0. And so G of 2 is equal to 0. You gotta subtract f of 2. You're in a graph of f of x equals 2, right? The point on the graph is right here. It has a y coordinate of 3. So f of 2 is equal to 3, and 0 minus 3 is negative 3. Okay. Any questions on that so far? Now we have a composite of G with itself at x equals 1. So by definition, this is G of 1. So again, first step, find G of 1. So here in the graph of G of x at x equals 1, right? The point on the graph is at 1, 3. Right? The y coordinate is 3, so G of 1 is equal to 3. Now you gotta find the G of 3. So here's x equals 3 on the graph of G of x. And you see the point at x equals 3 is down here, and it has a y coordinate of minus 5. So G of 3 is equal to minus 5. Okay. Any questions? So you have everything you need to successfully complete the 2.6 homework that is due when? Tuesday night, right? Good times. So if you've been working hard all week, remember to have some fun this weekend. If you haven't been working hard all week, you gotta stay home and work on your math. Is there someone named Emma? You don't get a copy, right?
Did you download it to book?
It's on, if it's not, it will be.
It's not yet, so I do need one.
Okay. So remember to print it out. But I forgot to post it on Oaks. But I'll probably get it done today. All right, so this will be the last of the material. You get one, correct?
Mm-hmm.
This will be the last of the material before exam 2. this has to deal with inverse functions. Alright, so let's talk about the difference between a function and a one-to-one function. The definition of a function, right, for each x, there is exactly one y, okay? And given the graph of an equation, we can tell if y is a function of x by the vertical line test. Well, not all functions. Some functions are one-to-one functions, some are not. A one-to-one function, right, meets this definition, but it meets the additional definition that for each y, there is exactly one x. And for that, given the graph of a function, determine whether it's one-to-one, we have the horizontal line test, okay? Why is this important? Because we're talking about inverse functions, and only one-to-one functions have an inverse function. Okay, not all functions do. Okay? So in example 1, it says determine whether the given function is one-to-one. So in A, we have f of x is equal to x cubed plus 1. Well, this is a transformation on the cubing function, which you should know basically how to graph. And if you know the graph of the cubing function, right, snakes through the origin. But here we're shifting it up by 1 unit. So it'll cross the y-axis at y equals 1. This passes the vertical line test, right? So it's a function. But it also passes the horizontal line test, right? No matter where I draw the horizontal line, it's going to intersect the graph in only one place. So this is a 1-to-1 function. And so this function has an inverse function. In B, we have f of x is equal to x squared minus x. What's the graph of this function? It's a parabola, right? And this is just a crude representation of the graph, but it looks something like this. Goes through the origin, okay? That's the parabola, right? And you know the graph of a parabola passes the vertical line test. Vertical line test, right? So this is a function But is it a one-to-one function? No, because I can draw the horizontal line right here, and it intersects the graph in two locations. Over here, no matter where I draw the horizontal line, it intersects the graph in only one location. But here it intersects two. So that means for this value of y, there are two values of x. And there can only be one value of x. So this is a function, but not a one-to-one function. So this function has an inverse function, this one does not. Okay? Some functions have inverses, some do not. Okay? And that is what this statement down here is saying. The function f has an inverse function if and only if f is one-to-one. And so the notation that we use for an inverse function is to put a -1 in the superscript on the name of the function. So this does not mean reciprocal. Okay? If I have x to the -1 power, that means 1 over x. Okay? So again, in math, we use the same notation to mean different things. But if I put -1 in the superscript on f, that means inverse function. That does not mean 1 over f. It does not mean that. So don't think of it in those terms. Okay? It's notation for the inverse function of f of x. Okay? All right. The graph of the inverse function is a reflection of the graph of f about the line y equals x. So you're provided with a coordinate plane. And so I just made this up, so don't ask me where I got it. It came from my head. So here's our coordinate plane. And the line y equals x goes through the origin. And it kind of splits the first and third quadrants. Okay? Like it's actually this line here makes a 45-degree angle with the positive x-axis. Right? So this is the line y equals x. Okay? And so I just made up function f of x that is 1-to-1. In my function, right, it crosses the y-axis at the point 0, 1. And at x equals 2, the value of the function is 3. So this is the point 2, 3. Okay. And out here at -8, at the point on the graph is -8, 1/2. So when I fit a smooth curve, right, the graph looks something like that. Okay? So this is a graph of y equals f of x. Okay. Now, you can see it's 1-to-1, because no matter where I draw the horizontal line, it's only going to intersect the graph in one location. Okay? For each value of y, there's only one value of x. Okay? The neat thing about graphing, given the graph of a 1-to-1 function f of x, the neat thing about graphing the inverse function is you just got to switch the order of the numbers in the points to get the points for the inverse function. So 0.23 is on f of x. So when we switch the numbers, we get the 0.32, and that's on the graph of the inverse function. So here is x equals 3, and then here is x equals 2, or y equals 2. So this 0.32 is on the graph of the inverse function. 0.01 is on the graph of f of x. So when I switch the two coordinates, I get the 0.10, which is on the x-axis. And so that point is on the graph of the inverse function. Then out here we have minus 8 1/2. So when I switch those two numbers, I get the 0.1/2 minus 8. So here's x equals 1/2, and here's y roughly down here, minus 1/8. So here's the 0.1/2 minus 8. And now I just fit a smooth curve through those 3 points. And this is the graph of y equal f inverse of x. So it's hard to do it for me to do it by hand, but the graphs are symmetric to this y equals xy. Okay? The right half, right, is a mirror reflection of the left half, and the left half is a mirror reflection of the right half. So given a graph of one-to-one function, we just switch the order of the points in order to graph the inverse function. Okay, vice versa. All right. So if you flip your page over, we have properties of the inverse function. We're not going to go through all, you can read through these on your own, but the two I want you to highlight are number 1 and number 2. The domain of the inverse function is equal to the range of the one-to-one function f. And number 2, the range of the inverse function is equal to the domain of the one-to-one function f. Now the beauty of this is it's often difficult to calculate the range of a function, like the y coordinates. But we know how to calculate the domain of a function. So given the domain of one, we know the range of the other. Okay. And then number 3, you should also highlight, right? If we have the one-to-one function y equals f of x, that is equivalent to x is equal to the inverse f of y. Okay, so let me demonstrate that with just a simple example. Because that's what these inverse functions are all about. They work in reverse of their one-to-one function. So let's say this is property 3 that I'm talking about. So let's say we have some function, right? Y equals f of x, and it's 1-to-1. So it has an inverse function. Okay? If it happens to be true that the function evaluated at x equals 2 is equal to 3, okay? So if the function evaluated x equals 2 is equal to 3, and it's 1-to-1, then it has an inverse function, and it's true that the inverse function evaluated at x equals 3 is equal to 2. Inverse functions work in reverse order of their one-to-one functions. Okay? What goes in to the one-to-one function comes out of the inverse. And what comes out of the one-to-one function goes into the inverse. Okay? So if you know one equality, you know the other equality. Okay? Are you with me? All right. And then number 5, to verify that the inverse function, f inverse, is the inverse of f in the composite of the inverse function with the one-to-one function f, you just end up with x. Okay? And that's true for f inverse of f of x and f of f inverse of x. Okay? That's how you can demonstrate that given two functions, whether they're inverses of each other or not. Okay? So in example 2, you're given the function f of x is equal to 6 divided by x cubed plus 9. And without actually finding the inverse function, f inverse, we got to determine the value of f inverse of minus 1/3. So there is some value of x, and when you put in for x and f of x, this on the right hand side is equal to minus 1/3. What is that value of x? Well, so f of x is equal to minus 1/3 for what value of x? Okay? So let's replace f of x with what it's equal to, 6 over x cubed plus 9. And in solving for x, as I said, it's equal to minus 1/3 in solving for x. I thought it was faster to rewrite minus 1/3 as 1 over negative 3. Right? I can do that. Minus 1/3 is the same as 1 divided by negative 3. And now you got a fraction on the left is equal to a fraction on the right. Remember in high school, did you ever do cross multiply? Yeah, you can cross multiply to speed things up. The old cross multiply, if you remember. Okay. So when we cross multiply, we end up with, right, x cubed plus 9 times 1, which is x cubed plus 9. And 6 times negative 3, which is negative 18. And we just solve, right? We're solving for x. And so you move the 9 to the right-hand side by subtraction. If x cubed is equal to minus 27. And then you take the cube root of both sides, right? So you have the cube root of x cubed is equal to cube root of minus 27. Do I put plus or minus in front of the cube root? No. No, because it's odd. When do we put it in front of the radical? When the root is even. Okay? So we're left with x on the left is equal to what on the right? Yeah, negative 3. Yeah. So x is equal to negative 3. Okay. So what this tells us now, f of minus 3 is equal to negative 1/3, right? That's what we know now. Okay, I had to convince myself of that. So, since f is a 1-to-1 function, okay, we know that f inverse of minus 1/3 has to equal what? Negative 3. And we did that without finding the inverse function. Okay? We did that without finding the inverse function. Okay? So f inverse of negative 1/3 is equal to negative 3. Okay? We did that without finding the inverse function. What goes into the 1-to-1 function comes out of the inverse, and what comes out of the 1-to-1 function goes into the inverse. Okay? You with me? Alright, so I don't want to rush to the next example, so I'm going to give you a bonus. Let you out a little early, and we'll finish bottom of page 2 and page 3 on Monday, and that will be, this material will be on the exam on Thursday, okay?